Welcome to the Optimality Gap Podcast, brought to you by Clemson University Informed Student Chapter. Today, we have a distinguished guest, Dr. Adolfo Escobedo, Associate Professor in the Edward P. Fitts Department of Industrial and Systems Engineering from NC State University. Dr. Escobedo's research spans mathematical programming, algorithm design, and computing with application in power system sustainability, computational social choice, and computational linear algebra. His work has been recognized with multiple honors, including the NSF CAREER Award and the Informs Computing Society Prize. Thank you for joining us, Dr. Escobedo.
Thank you, Jahid, and thank you all at the Clemson University Department for having me.
Let's begin with your academic journey. You earned your PhD in Industrial Engineering from Texas A&M University and BA in Mathematics from California State University. So what initially drew you to mathematics, and what motivated the transition towards operation research and industrial engineering?
All right. Well, the shortest one, the shortest answers right first, right? Because this one's gonna take a while. We'll see about the other ones.
Yeah.
So, in terms of the journey, what got me interested in mathematics? Well, I would say I've always been interested in mathematics.
Mm-hmm.
But in high school, I only got up to like algebra 2. I was working and doing things, so I didn't get a chance to take higher level math. So fun fact, I actually started my university journey as a history major. Sorry, not a math major. I was a history major, so I did that for like two and a half years. And at the same time, I always had this itch, that
Quite interesting.
yeah, that I wanted to keep going on mathematics, because I had heard that calculus is the highest level of mathematics we can read that you could reach, and I wanted to know what that was all about. And of course, that's like it's the opposite, right? That's kind of like the basement, right? And then you go up to the two different types of math. But no, I like history. I've always loved history, but at the same time, I had this itch for mathematics, and I really wanted to pursue it. So at the same time as I was majoring in history, I was taking more and more classes at the same time. Mm-hmm. And then I just kind of, one day I just had an epiphany where I was like, I really need to switch over to math, like full time, not just like have it be a hobby, because it was just a lot more stimulating for me. I love history, like I said, but I saw that as first I saw it as kind of potentially limiting my options in what I could do professionally. Mm-hmm. Right? It's not impossible for people to enter academia in history, right? But it's very competitive, and there's not that many positions out there. And you could also, the typical jobs for somebody with a history degree is like you either continue into academia, or you can teach high school, which there's nothing wrong with that, but I kind of wanted to do something a little bit where I could also do, my own investigation, right? And that's easy to do.
Really fascinating story. From history to mathematics.
Yeah, exactly. So from history to mathematics, right? And so anyway, so I wanted to expand my options, right? So then I went into mathematics, but then at the same time with mathematics, I saw the beauty of it and the elegance of it, and I really like, the concepts and getting to know that there's more than just calculus out there, right?
Yeah.
And but at the same time, kind of similar with the career choices, I really wanted to do something where I'm going to be able to not only solve problems, but I'm going to be able to solve problems that are relevant today, right? Maybe not decades from now, when some of the abstract math that I will be studying will be relevant.
Yeah.
But in the near future. So then I started doing my research after I graduated. I looked at different fields where this could be useful, like a mathematical skill set like this. And lo and behold, I landed on industrial engineering, which I knew nothing about. I never took a class on linear programming in undergrad or anything like that, so I had no idea what it was. But I kind of just fell in love with it, and then I haven't looked back since.
Interesting story, I must say. So, how did your background in pure mathematics help to think about the problems in operation research or industrial engineering?
Another interesting question with a potentially long answer. So I would say that mathematics was helpful, but at the same time it did give me like a false sense of confidence, right? That I was going out there and I was going to, because I'm trained in mathematics, pure mathematics, I'm going to be able to just get plugged in and I'll be able to, just kind of relax in the classes, not pay that much attention, that kind of thing, just kind of breeze through. But it was quite the contrary, in fact, because there's an art, right, to industrial engineering. I would say in particular, starting with modeling. This is not something that you really learn in math. Perhaps you learn it maybe in physics to some degree, right? Yeah. But you don't take too many courses in that area as a math major. So I would say it prepared me eventually. Like at first, it was like a real culture shock, like academic culture shock to go into the classes. Like I said, I never took a class on linear programming, nonlinear programming. So seeing that for the first time, the notation with the summations and everything. Nowadays, if I look at it now, it's trivial, right, to read that stuff. But even as somebody trained in mathematics, if you haven't seen it before, like a constraint given in an oral form translated into mathematical form, it takes a while to get used to. So I would say it was useful eventually, because then the skill of mathematical proofs and mathematical reasoning that came in later in the research part.
Yeah, I think most of the IE PhD students, like when they move from IE undergrad and graduate background to PhD program, I think they struggle with real analysis or mathematical proof, this kind of thing, where I think math majors thrive.
Yeah, I would say, but it's something you can pick up, just like you can pick up modeling skills, same thing in math. And I would say I wouldn't even exaggerate it too much in terms of the mathematical reasoning, because then a lot of times, in undergrad, you're taught to memorize things, right? So you can do a proof, but a lot of times you're just regurgitating the proof from the book. You're not really thinking about, the logic, the reasoning, right? A lot of times you're just kind of memorizing things, whatever the professor said, that's what you memorize, right? That's what's tested, right? And I think that's when you actually apply it to something new, something that is unknown, it's a total, different ballgame.
Yeah, we need to think more problem specifically. So your research portfolio spans several domains. So what unifies these traits in terms of methodological approach or theoretical contribution?
Well, I would say the connection in terms of methodology, there's some connection there, but I would say the connection is what interests me, I'm a very curious person, like I said, based on my, as you can see from the different things that I studying history and then math and engineering and so forth. So it's just different things that interest me. I would say the unifying material or whatever would be things that are interesting to me, but I also try to work in areas where I think that something has been overlooked. We need stronger guarantees for either an algorithm or some kind of methodology that is utilized in practice.
Yes.
And so I want to develop these rigorous methods for applications where this has kind of been or hasn't been looked at as much. I wouldn't go so far as to say that it has never been done, but I want to kind of look at the fine details to make sure that we can achieve the guarantees that we are claiming, either computational or, like I said, or theoretical. From a computational point of view, right, you can talk about ensuring that optimization solvers, when they tell you that a solution is optimal, that it's actually a valid output, right? That it hasn't been affected by numerical errors, right? From a theoretical point of view, is you are sometimes there's claims something about the optimal solution being able to accomplish something. For example, in social choice, that you're showing that, hey, this ordering of candidates that I'm giving you in a social choice context is guaranteed to be the closest to what everybody's votes are, right? So you can show that, you can establish that. So that's kind of the stuff that I'm interested in. kind of look at these things that people have looked at for some time, but then, kind of look a little bit closer under the hood, so to speak, to try to, fortify those guarantees.
Yeah. So another application area you have is optimization for energy and sustainability. So you have studied challenges like robust transmission expansion under rising temperature. So what unique modeling and computational difficulties arise when linking optimization with climate and sustainability concerns?
Well, I would say that, in that particular problem, typically in power systems planning, for the most part, you want to plan into the future to satisfy future demand, right?
Yeah.
And people have thought about, demand is going to not be static, right? It's going to grow and it might be uncertain, right? There's uncertainty, so we don't know these things. We have expanded the modeling skill set to reflect that, right?
Yeah.
But there's other things that what we try to look at there is try to think about other aspects that have not been considered, right? So one of those aspects was just at the transmission level.
Yes.
If as we're seeing the trends in hot temperatures rise, heat spells that last longer and longer.
Yeah, recently we see this.
Yeah, this is going on, throughout the country, and,
Yes.
and like I said, I used to live in Arizona, so I can tell you
Yeah.
about a bunch of unfortunate streaks we had while I was there.
Burns the screen.
Yeah, exactly. But for power systems, what happens is that when there's heat, ambient heat, and it's high and it holds on for long, then this degrades the ability to deliver electricity according to whatever the design is of the system.
Yeah, I can remember from my electrical engineering class.
Well, the wires, right? The
Yeah.
wires that are out there to transmit electricity, they're rated for ambient temperature. So when there's heat out there,
Yeah.
then that will degrade the performance. So sometimes the system operator will actually, on purpose, they will load the transmission lines at a lower level, right? Because they don't want to damage them.
Yeah.
So implicitly, right, this degrades the ability of the power system to perform well, right, to deliver electricity.
Yeah, that's true.
So that's what we looked at. We looked at this. We had some ways to model how the temperature is kind of rising in time to try to plan for these scenarios. And then we also looked at providing different options for overcoming this. So one of these options is conventional expansion planning. You invest in transmission lines, and another is that you make the lines, you reinforce them so that they can withstand high temperatures. That's a little bit more expensive than a normal line, but we kind of experimented with that.
So in this kind of applications, do you see that OR scientists and OR researchers, they are developing this kind of methodology, but are those methodologies are being implemented in the real field? So has we reached in this kind of situation?
Well, I would say yes, but maybe not at the level that we would like, right? So this is kind of related to this concept of the smart grid, right? We've been talking about that for at least a couple of decades now, right? About you being able to use the grid in a more efficient way, right? Integrating new devices. So more and more we're seeing the technology kind of come in and provide more flexibility for the grid, but I would say that there's still a little bit of reticence, to adopt everything that is out there, right? So one, common example that people give is just using renewables, right? Being able to integrate renewables, right? That has grown, the capacity has grown, but because of the concomitant uncertainties that come with it, right? Then you can only plug in so much without running a risk, right?
We see
That's how
new
people
challenges
perceive it.
recently because of the data centers, huge demand just arise in random locations. So suddenly they install a data center, so the demand also.
I think it's only going to, that's going to get worse now, right? Because we're seeing,
Yes.
these data centers, they're consuming as much electricity as a small city.
Yes.
Yeah. So I think now more than ever, we need people, working with our skill set to think about how this is going to, further stress the grid, right? More than it already was.
Yeah, I think there are a lot of challenges coming like this. Nobody thought about this problem, I think 5 years ago, but
Yeah. Yeah, now it's on everybody's
yeah,
mind.
on everybody's mind, yeah. So a theme that stands out in your work is methodological diversity, polyhedral theory, algorithm design, heuristics, and data-driven approaches. How do you decide which methodological tool is most appropriate for a given research problem?
Well, I would say, you let the decision come to you, kind of based on, how what the problem is, how difficult it is. Yeah. We try to start from, try and rely on things that we have done in the past. I was like, hey, we've, dealt with cutting planes before. We have the composition methods that we have developed, so we look there. But sometimes, we need to adapt, right? If those things don't work, or maybe they're not as good as we hoped, right? Then we need to pivot, right? So I would say it's kind of driven by the problem. Obviously, I try to work in things that I'm familiar with, and or we kind of learn it. I don't want to get too far from what I know, right? Like quantum computing, I probably won't be able to do that tomorrow, yes. Right? But maybe the students, because that's who drives it, really. The students, like we guide the students to try different things, and then sometimes, they also come up with something innovative, and then, I learn as they're learning.
Yeah, that's true. I think that's also like there is also a learning curve for the PhD student also. So because we can spend more time on a particular problem, so and that helps. So looking more broadly at the field of operation research, how do you think the discipline has evolved over the past decade?
Well, I guess I could give you maybe my perspective, but I would say that obviously there's more emphasis on data-driven approaches, right, in operations research, and I think that's going to continue. That's going to continue growing, right?
We see this keyword in the title. Keyword section.
But at the same time, there's also a lot of interesting work going on where we're trying to integrate, right? Kind of like the more traditional approaches and like the data-driven approaches. Like, there's work out there, in the last decade or so about prescriptive, predictive modeling, and kind of maybe utilizing the tools of machine learning, right, to improve
the optimization.
Like traditional algorithms, right? Maybe not for like a specific application, but you probably have seen some work recently where they're using machine learning to modify like branch and bound, right? Like how to select the entering variable, how to select the branching rule, and so on, right? So I think that this integration is going to continue. So I still, even though there's an emphasis on data-driven approaches, and that's a trend, I think that, the classical approaches are still going to be relevant, right?
Yeah, I think people are also trying to solve graph problems using machine learning. And so do you think like is this just a hype, like people, as every sector is trying to apply machine learning and AI in their areas, so some OR researchers are also trying to implement machine learning or AI algorithm in the research. So it's just a hype, or it's a real thing that's gonna last?
Well, I think the time will tell, but I mean, intuitively, I would say that there is no reason to think that it's not going to continue to be relevant. I mean, yes, maybe there is a bit of a hype to it, but is it warranted, right? I do think it's warranted because we're seeing what is possible out there, right, from data, right? Not just in machine learning, but obviously AI, right? There's things that we didn't think about 5 years ago that are now here, right? And some that we haven't even dreamed, right? That will be here tomorrow, right? So I think machine learning is going to continue to be relevant, but at the same time, like I said, I don't think that this means that classical OR approaches are also going to go by the wayside.
Yeah, so there are a lot of like industry push, and I think expectation from practitioners that they also can use the machine learning tools. Sometimes, like recently, Gurobi published a module, so you can use GPU for solving maybe MIOP or this kind of problem. So I think there is also a push or demand from everyone.
Yeah, yes, I think we're seeing integration there as well, right? Like in terms of computational paradigms, right? GPUs, people have for a while they have kind of thought that they were relegated mostly to machine learning, right? But now we're seeing that there's no reason to think why they couldn't also be used for something like optimization.
Yeah, so I think that would be really interesting to see how that works. So, like it's a different time. Even the employer are talking a lot about machine learning. So, what skills or foundations do you think are most crucial for graduate student in OR today?
Well, kind of harking back to the previous conversation, you definitely want to start by learning about the Roman Empire.
Yes.
Just wanted to throw a curveball out there.
Yes.
No, the foundations, right? The foundations, I would say you want to start, obviously with math, right? Mathematics, mathematical reasoning, I think now more than ever it has to be kind of integrated more into the curriculum, especially because now we know that there's tools out there that can do, many of the things that we would have to do before, right? Like data analysis, basic computations, right? All these things can be done automatically now, right? But mathematical reasoning, at least for a little while, I think it's going to differentiate us. So I do think that mathematical reasoning, and obviously to be able to apply mathematical reasoning, you need some sort of methodological foundation.
Yeah, I agree with your thinking, because recently some famous people like the CEO of NVIDIA, he mentioned that it's a good time to learn math or basic science like biology or chemistry, physics. So I think interesting time. I think 5 years ago, people only thought like you need to be really good in coding or this kind of thing. But after 5 years, it's a different story, right?
That kind of got flipped on its head, right? We're telling people that need to learn how to code, and then maybe they coded too much, right? I don't know. They coded too much because all the code that's out there was used to kind of replace the coders, right?
Yes.
We're still in the middle of it. We'll see to what degree this is going to reduce the need for coders, but yeah, what's needed? I mean, even the experts in AI, they can't really tell you, right? Everybody's guessing, but I think based on where we're sitting, right? I think that focusing on the math and the foundations, which is kind of the strengths of our field, I think, is a good strategy.
Basic is really important.
Yeah,
knowing the story of Roman Empire. So, as we wrap up today, what are some of the big open problems in OR that excite you the most for next 5 to 10 years?
Wow. Okay. Well, many different directions that can be taken there. I'm really interested in trying to ensure, like I said, that the outputs of optimization solvers are valid or accurate, right? But to do that, we have some math that can do that already. We have some methods that can do that, but we need to bridge the gap in terms of being able to have these robust tools can be utilized. We need to bridge the gap between just having them there to actually being able to scale them up for them to be competitive against commercial or standard floating point solvers, the ones that may not give you those guarantees as easily. So in order to get from here to there, specifically like let's say in the area of mixed integer programming, we still need a lot of work to do, like how to leverage some of these robust methods in that space, how to be able to do it in a way that you make efficient use of memory, efficient use of computation. So there's a lot of open questions there, and I'm hoping that I can at least contribute to some of them.
We wish you best of luck for that. I hope you're gonna come up with new studies and breakthrough that's gonna develop our fields a lot. So Dr. Escobedo, it has been a real honor speaking with you today. Thank you for your time today, and thank you for visiting Clemson and give us some time for this podcast episode. I hope you enjoy your stay in Clemson.
Thank you.
Thank you.
Thank you very much.